Help you understand how important the coordinate plane is in math. It's one of our most important tools, and it can really help us. So let me start by discussing how it kind of came about over time. First of all, you had map makers back in the before Christopher Columbus's time who would make maps, and they realized that in order to identify a point on a map, you would have a grid system. So that's kind of where it started. But in the 1500s, it really took off with a young fellow named Descartes, or his real name is Descartes. It was a French name. And he was a young man, and the legend goes he was a mathematician and a philosopher, but as a young man, he was kind of a sickly boy, and his schoolmaster let him sleep in. And he would sleep in late and just sit in bed and think. And one day he was looking at the ceiling, and he noticed a fly on the ceiling. And he started wondering to himself, how could I describe the location of that fly? And then the fly got up and he flew around and he landed again on the ceiling. And then he thought, how could I describe the location of him there, and how would those 2 points compare? And so before long, he had started thinking in terms of a number line. So maybe this is 1 or 0, 1, 2, 3, 4, 5, 6. So he's making a ceiling into kind of a grid. And then he's making a vertical and a horizontal number line. And then you could say that the fly is at the point 1, 1 or 4, 2. And someone would be able to understand what he was saying based on those ordered pairs or coordinates. So that's kind of the legend behind the coordinate plane. They even call it the Cartesian coordinate plane. Let's take a look at what good it does. First of all, I want to talk about function. So function is when you compare two variables and one variable has some kind of an effect on the other variable. The dependent variable depends on the independent variable x. So look at this first graph here, this first coordinate plane. As x increases, as time in minutes increases, the water left in the pool in gallons is going to, if you're draining it, it's going to decrease. And it might decrease kind of like this, because as it drains, there's less and less pressure on the water coming out of the drain. And so there you have it. And this kind of tells us a story. It tells us that we're going to lose a lot of water at first, and then it's going to take a little bit more time as a lot of the water is already lost. And the other thing that it does is you can plug in an input. Say maybe after 1 minute, you are at so many gallons, or after 2 minutes, you're at so many gallons here. So it tells us a story, but it also gives us an idea for exact input, how much an output is. Let's take a look at the next one. We've got dollars earned and hours. So typically when you're working, if you are working at an hourly wage, after 1 hour, maybe you have $10. After 2 hours, you have $20, and so on. So this graph is saying that you get the same amount per hour. You go over the same, up the same, over the same, up the same. It's a linear graph, a linear coordinate plane. And it's also saying that you can plug in the number of hours, x, plug that in, and get out the number of dollars, y. Okay, let's take a look at the last one. Height in seconds. If you were to throw something up in the air, its height's going to increase quickly at first because of that initial force that you used to throw it, but then gravity is going to take effect on it, and it's going to come to a standstill eventually. And then gravity is going to keep working, and so it's going to start slow at first and then kind of speed back up again. So there's a story for that coordinate plane. And again, as you have one input, you can determine output. Maybe after 1 second, your height is so much, and after 2 seconds, your height is so much, and so on. So coordinate planes are helpful in looking at functions and recognizing the patterns, but also recognizing your output when you have a given input. Let's go to the next page. Systems of equations. This is when you have more than one equation or function on the same graph, and you're starting to compare or look at them. One of the big things might be the intersection point of those two equations. So let's look at this word problem. Ryan starts at 12 noon and drives 50 miles an hour. Beck starts at 1 o'clock an hour later and drives 60 miles per hour. When will Beck catch Ryan? Well, let's graph Ryan's. We've got 1 hour is at 50, 2 is 100, 3 is 150, 200, 250, 300, so on, something like that. So 4, 5, 6. And then we have Beck. He starts an hour later, and so from hour 1 to 2, he's at 60 miles. And from hour 2, he's at 120. And from the next to the next, he's at add another 60 to 120, you get 180. And then add another, you get 240. And then finally at 300. So you'll notice that, let's do Ryan's in pink right here. And then let's do Beck's in red right here. You'll notice that Beck eventually catches Ryan right there. So this is a system of equations. You're graphing two equations on the same coordinate plane, and it's identifying an intersection point for us. So this is kind of helpful to have a coordinate plane there as well. Let's take a look at another example of where a coordinate plane might come in handy. Here we have data points. So it says years of schooling and salary. So a person who has a lot of schooling, way over here is this data point here represents him. He has a high salary. Person who has very little schooling right here has a lower salary. And you take all those data points, and using a calculator or a more advanced mathematical technique called least squares regression, you come up with a line that is as close to possible to all those points right there. And then it's a function, and you can kind of determine after so many years of schooling how much the average person makes or what the salary would be. Another feature of scatter plot is you can also determine how good your line fits this data by looking at something called a correlation coefficient, and that measures the distances of all of these points from the line collectively. Okay, let's look at one more. What if you had some data on age and car accidents, and you noticed that 16-year-olds, 17-year-olds tended to have more car accidents, and then it kind of leveled off, and then as people aged again, maybe it got higher, and you recognize a pattern. Again, you could write a equation based on these data points. This would be a regression equation, and then you could put in an age and get out an idea of how likely that person is to get in a car accident. So scatter plots are coordinate planes that use data points, and this is kind of the basis for statistics. Let's look at some geometry for a second. Geometry, lines and line segments are kind of a big deal. So you could plot 2 points on a plane, and then you could use some, slope is rise over run. You could use that information and make yourself a little bit of a slope triangle, a rise there and a run there, and you could determine the steepness of that line. It would be y2 minus y1, I hope this is a little review for you, over x2 minus x1. Okay. You could also determine the length of that line using the Pythagorean theorem, but the Pythagorean theorem on a coordinate plane. So again, this is this part right here is y2 minus y1, that's x2 minus x1. So we put, if the Pythagorean theorem is a squared plus b squared equals c squared, then x2 minus x1 is the same thing as a, and y2 minus y1 is the same thing as b. And then we got c squared, and we have to square root it. That gives you the distance right there based on those points. And if these points had a numeric value, you could find a distance for any line segment. So slope, distance, and finally the midpoint. You could also find the middle of that line segment if you folded it right in half where it's at. Using the midpoint formula, it's just the average of the x's. So x1 plus x2 over 2, and y1 plus y2 over 2. And that is the midpoint right there. So the coordinate plane, once again, very helpful in geometry, dealing with line segments. Let's take a look at something a little bit more advanced in geometry, proving properties of geometric shapes. In front of you, you'll see a rectangle that I've put on a coordinate plane. And the question is, are the diagonals of a rectangle congruent? Can you prove it? Well, I've given some ordered pairs to the vertices of this rectangle: 0, 0, x 0, 0y, and xy. And you'll notice that that these ordered pairs should make a rectangle. Now all we have to do is use the distance formula for the green and see how long that green diagonal is. So I have 0y and x 0. So we go x2 minus x1. That's going to be x minus 0 squared. And then y2 minus y1. So 0 minus y squared. And then we square root it. This is the distance formula that we used in the previous slide. So x squared plus negative y squared is that length there. And this negative becomes a positive when you square it. Let's take a look at the red line for a minute. We have the point 0, 0 and the point xy. And we're going to go x minus 0 squared plus y minus 0 squared. And we square root that, and we get x squared plus y squared. And with the exception of this negative right here, these are the same exact things, and when you square a negative, it becomes a positive. So yes, the green line and the red line are congruent to each other, and we've proven that for any rectangle using the coordinate plane. Okay, number 6 is going to be about trigonometry, and I'm going to save that one for the next video, but I do want you to be aware that the coordinate plane just comes up everywhere in math. It will not go away. It is a wonderful tool. It can really help us understand relationships and things, and I hope this has been a little bit helpful to you. Thank you.